Dobry wieczór. Copernicus Festival 2023 Kosmos. Witam wszystkich Państwa tu na żywo zgromadzonych w Muzeum Inżynierii i Techniki w Krakowie, jak także wszystkich tych, którzy oglądają lub będą oglądać nas zdalnie. Czas na wykład kolejnego naszego głównego gościa, a ponieważ nasz główny gość jest Brytyjczykiem, to pozwolę sobie od tego momentu przejść na język angielski. Ladies and gentlemen, good evening. This is Copernicus Festival 2023 Cosmos. It is my great honor and privilege to welcome our main guest and lecturer tonight. And this is Professor Bernard Carr, who is Professor of Mathematics and Astronomy at Queen Mary University of London. He obtained his PhD in relativistic physics and cosmology under the supervision of the great Stephen Hawking, and his main research interests include early universe, black holes, dark matter, the anthropic principle, and the multiverse hypothesis. He's also interested in the role of consciousness, which he views as a rather fundamental than just an incidental feature of nature. Professor Carr looks at the cosmos from many different angles. What does he see? Let's find out. Professor Carr, welcome. The floor is yours.
Thank you very much, Thomas. It is a great pleasure to be here to talk to you. I first came to Krakow 50 years ago for my first conference. And it was a pleasure then, and it's a pleasure to return now, 50 years later. I should say that I've got a rather croaky voice. I'm suffering from laryngitis, so I'm hoping my voice will last throughout the talk. If it doesn't, my wife is here, and she can take over. Now, my title is The Cosmic Uroboros, Linking Microphysics, Macrophysics, and Mind. I don't know if you're familiar with the image of the cosmic Uroboros. You can see it in front of you. It's the snake which is swallowing its own tail. And I'm going to explain why that is very relevant to describing microphysics and macrophysics. And at least the first half of my talk is going to be about straight physics, because I think that's what this festival is celebrating. But I do also want to get on to the topic which interests me and maybe interests you, of mind. And I'm going to argue that mind is really important, even though physics sometimes tends to push it to one side. So, just to say a little bit about the Uroboros. The Uroboros is a very old symbol. It appears in many, many different cultures. It's sometimes interpreted as an archetypal symbol. And you can just see a few examples here. I'm not going to go into this in great detail. It's always the snake which is swallowing its own tail. And you can see the various forms here. And in this one is quite nice. It's got a man in the middle. There are even figure of 8 forms of the Uroboros. But I'm not going to say too much about that, except to say it is for some reason, it seems to be a symbol which appears in many, many different cultures over many different eras. But I'm going to actually focus on the Uroboros in a very specific context. I'm going to focus on what is called the cosmic Uroboros. And I will explain what this diagram is. It's got quite a lot of information in it. But the point about this is that around the body of the snake are the various levels of structure which are observed in the universe. So you have microphysical structures on the left, and you've got macrophysical structures on the right. And the point about this diagram is that it's like a ruler. And as you go from the top left to the top round in an anti-clockwise direction, I'm not even going to try and use this pointer, to the top right, the scale increases by a factor of 10 for each minute. So actually it's like a clock, and it is 60 decades of scale. The smallest scale at the top is what's called the Planck scale, at the top left. On the top right, the larger scale is the scale of the observable universe. So if we look at the bottom, we have human beings, and as you go to the right, you get successively larger objects, so you have mountains, planets. They can't hear.
Yeah, they can't hear when you turn around.
Oh, thank you. Sorry, you can't hear when I turn around. Okay. I won't use this pointer, it's a bit distracting. So you've got mountains, planets, stars, galaxies, and the universe itself. As you go to the left, you get successively smaller things. So you have ants, amoebas, DNA, atoms, nuclear particles, and then at the top right, you've got all the particles predicted by subatomic physics. And why I like this diagram, it not only represents all the different levels of structure in the universe, in some sense, it represents, you can use it to represent the history of physics as we've expanded our knowledge to ever larger and smaller scales. Obviously, we've used things like telescopes to probe ever larger scales, and you can think of that as, if you like, an outward journey. And then there's an inner journey where we use microscopes and particle accelerators to probe ever smaller scales. And so you can think of the history of physics as the expansion of our knowledge, consciousness, if you like, to ever larger and smaller scales. So what I'm going to do in the first part of my talk, I'm going to take you on a journey which is going to describe the history of physics on first the outward and then the inward journey. So I've got quite a lot of material to get through, but I think you're probably familiar with quite a lot of it. So if we set out on the outward journey, as I'm sure you're aware, if you go back a long time to the days of the ancient Greeks, it was thought that the earth was the center of the universe. And indeed, there was a distinction between the earth and the nearby regions where there were planets moving, and the outer regions where the stars were. The stars were assumed to be the domain of the divine. Close by the planets, things moved because that was mortals, but the stars never changed because that was the domain of the divine. And so here is the standard image with the earth in the middle and the planets revolving around the earth, and of course the sun is also revolving around the earth in this view. But the fixed stars at the outer edge, they don't change. Well, as you all know, that picture changed dramatically when Nicholas Copernicus, to whom this festival of course is dedicated, he realized that the earth goes round the sun, not the sun going round the earth. And as you know, we're celebrating his birth, which was exactly 550 years ago. But in some sense, his birth is also going to represent the first step in this journey I'm going to take you on. So there is our image of the heliocentric view with the sun at the middle. And 1542 is when he published his work, in fact, just before he died. Now, another important person was Tycho Brahe, who was just after Copernicus. Tycho Brahe was one of the first observers. He had his own telescope, and he made observations of planets, which were going to become very important in developing our theories. But what I want to particularly tell now is a story. One night in 1572, he was taking a walk, and he came from Denmark, and he saw a bright star in the sky. Now, it turned out that this was what we now call a supernova. It was actually an exploding star. But what he noticed over the following months is that the position of this, it didn't change. Okay? Now, normally, if something is nearby, you expect its position to change. As you move around, as the Earth goes around the sun, you expect the position to change. But he noticed that for this object, it wasn't changing, and he knew from that it was at a great distance. However, that was impossible because according to the traditional view, the stars never changed. So it would be all right for something nearby, like a planet, to move, but you can't have something at great distance. Actually, and it was at a great distance because it didn't move. So nobody believed him. He said, this can't be true. And he said this famous remark, crassa ingenua o cocus coeli spectores, which means, oh this blind watchers of the sky. Because there was the evidence, this supernova this light in the sky which was at great distance. And they wouldn't believe the evidence because the Greeks had said, if it's the heavens, the stars can't change. So there's a lesson you can draw from that. Your theoretical prejudice should not blind you to the evidence. And this is a message which is going to be true throughout the history of science. And so that had demolished the view that the stars never changed, which was required if it was the domain of the divine. Then Kepler came along, and Kepler was able to use the observations of planets by Tycho Brahe to deduce the laws of planetary motion. I won't go into the details, but he found that planets moved on ellipses and things like that. And then, of course, the other important person was Galileo. And Galileo played a crucial role because he had the telescope. And he was able to find all sorts of things with his telescope, like the sunspots on the sun, showing the sun changed. And he could observe the moons of Jupiter and things like that. But also, most importantly, he discovered things about the law of gravity by throwing balls off the Leaning Tower of Pisa. As we all know, he got into trouble with the Pope because he also was an advocate of the heliocentric view. And, well, I won't go into the long story of how he had to recant and things like that. But if you like, it was the start of the tensions between science and religion. But he played a crucial role in the development of science. And then maybe the most important development of all, Isaac Newton, who was actually born just as Galileo died. Isaac Newton, of course, wrote his important work Principia, which was really the start, in a way, of modern science. And he formulated the laws of mechanics. He discovered the force of gravity. And in a way, that was the start of modern physics. Now, those four works by those four people, I had the great pleasure to be able to see when I visited Turin only about maybe 8 years ago. I went to the house where Copernicus was born. And there you can find the four works by those four people, Brahe, Kepler, Galileo, and Newton. And they're all in this case. And it's just amazing. You look at this bookcase and you think, these are the four books which really are the foundation of all of astronomy, and indeed all of physics. Now, even though Galileo was aware there were other stars, he was aware that our sun was just one of many stars in the sky, people were very skeptical that science could be applied to beyond the solar system. Auguste Comte was a famous French philosopher, and he said in 1859, never by any means will we be able to study their chemical compositions. the stars, that's to say. The field of positive philosophy lies entirely within the solar system, the study of the universe being inaccessible in any possible science. So basically he was saying, we agree there are things beyond the solar system, it will never be part of science. However, just a few decades later, they discovered spectroscopy, which enabled you to get information about the stars from studying the light which was emitted. So there's a lesson to learn there too. New observational developments are sometimes hard to anticipate. He was rather unlucky because he was disproved within just about 10 years. But that's still true today. You still have people saying, this isn't part of science, because they don't anticipate just how good science is expanding, the ways in which it can probe nature. But then, but certainly by the beginning of the 20th century, we had the galactocentric view, which says that the universe is not just the solar system, it's all of those galaxies, all of the stars in the galaxy. And our galaxy is called the Milky Way. This is actually the Andromeda galaxy, but ours looks pretty similar. Of course, when we see the Milky Way, we see it from inside, and we see this band of stars in the sky, which I'm sure you've seen at some point. It took a little while before we came to realize the precise nature of the Milky Way. The very first model, the Captain Universe, because to them it was the universe, the Captain Universe in 1913 had the sun at the center. So we were still very much in this, trying to make us as central as possible. We now know that, in fact, the modern view of the galaxy is that we're sitting in the disk, and we're something like 8 kiloparsecs, that's the unit we use, 24,000 light years from the center. But that's a detail. The point was, at that time, people assumed the galaxy was the universe. It wasn't clear there was anything outside the galaxy. However, people had speculated about that, and many eminent physicists did not react well to the idea there could be something outside the galaxy. Here's Rutherford at Cambridge. He said, "Don't let me hear anyone use the word universe in my department." That was the Cavendish. Well, there was a great debate in 1921 about whether there was anything outside the galaxy. Because, of course, you could see these nebulae in the sky, but we didn't know whether those nebulae were in our galaxy or outside the galaxy. And there was a great controversy, and Harlow Shapley, he was arguing that it's unlikely that any of these nebulae could be outside the galaxy. On the other hand, Heber Curtis, he led a group of people who supported what's called the island universe idea, the idea that some of these nebulae were other galaxies. I should say that this had been suggested. I mean, even the famous philosopher Kant a long time ago had talked about the possibility of island universes, but it was a minority view. By 1921, it was an intense debate. The debate was indecisive, but just a few years later, the debate was resolved. And that was because Edmund Hubble was able to measure the distance to M31, that's the Andromeda galaxy. In fact, I showed a picture of that in a few slides back. He was able to measure the distance. And he measured the distance by using what's called a Cepheid star. I don't want to go into the details, but a Cepheid star varies in intensity. And there's a link between its brightness and the period. So if you measure the period, you can tell how bright it is and therefore how far away it is. The further away it is, the dimmer it is. And so he was able to measure the distance of the Andromeda galaxy. It turned out to be 500 kiloparsecs. That's what he measured. A kiloparsec is 1,000 parsecs. A parsec is roughly 3 light years. And that was well outside the galaxy. So that was a huge development because it showed that our galaxy was not the universe. There was a whole big world out there. Now, he then went on to discover something even more important. He started studying the galaxies, and he found something rather strange. He found that the galaxies all seemed to be moving away from us. And furthermore, they were moving away with a speed proportional to their distance. And here's the original plot from 1929. You've got the velocity on the y-axis and the distance on the x-axis. And the data's a little bit ropey. He'd only got a few dozen galaxies, but he guessed that was a straight line. And that's called Hubble's law. The velocity is proportional to the distance. Now, many decades later, we had a much better version of that diagram. And you can see that it does indeed look like a straight line. I should say that you measure the velocity because you can measure what's called the redshift, the shift in the wavelength of light. And that's how you measure the velocity. You measure the distance because you measure basically how bright the galaxy is, and that tells you the distance. Now, just to show what a big development that was, the original measurements of Hubble were just that little red patch in the left-hand corner. So it was really a guess. He could have been wrong because it was very little data in those days, but it was right. It turned out this was the straight line. And that is fundamental to cosmology. So Hubble's law is, I said the velocity is proportional to the distance. More precisely, we say the velocity is the Hubble constant times the distance. So that's, the Hubble constant is what Hubble and other astronomers later measured. And the inverse of the Hubble constant is a time scale, and it's roughly 13.7 billion years. And that is when the Big Bang was. Because if the universe is expanding, when you go back in time, you expect everything to start in a very compressed state. And that simple formula tells us that the time of the Big Bang was roughly 13 billion years ago. And that's nice because it is also, roughly speaking, the ages of the oldest stars. Now, why should the universe be expanding? At first, you might think that all the galaxies were running away from us. But actually, what is happening is that space itself is expanding. And this had been predicted by Einstein's theory of general relativity, which was in 1916, so that was 10 years earlier. And the simple way to understand this, you imagine someone blowing up a balloon, and you paint the galaxies as points on the balloon. The blowing up of the balloon is the expansion of space. And all the galaxies seem to move away from each other. And so there's no actual center of expansion. Every galaxy can review itself as the center. And Hubble's law is a natural prediction of that expansion. So this was actually predicted by Einstein. Einstein himself did not predict it, because Einstein thought we were still living in a static universe because he thought the universe was the galaxy. Remember, relativity was in 1916, and we didn't discover Hubble's law till 1929. However, there was a Russian physicist called Friedmann, and he did realize in 1922, before Hubble, that Einstein's equations predicted an expanding universe. And indeed, he realized that this expanding universe could have various futures. It could either recollapse or expand forever. And cosmologists have always been interested in that ever since. But Einstein himself didn't believe Friedmann. But Friedmann was able to use Einstein's equations to prove that. But the really interesting development came in from when George Lemaitre, who was a Catholic priest, an abbé, and a cosmologist. He actually realized that Hubble's law implied that as you go back into the past, the density gets bigger. The universe must have started with a very condensed state. And so he's sometimes called the father of the Big Bang. He was the first person to realize that. He didn't use the phrase the Big Bang, but that's what we would now say he was referring to. It's interesting, Lemaitre was a cosmologist and also a priest, rather like Copernicus himself, who was both an astronomer and I've actually forgotten what his denomination was within. Anyway, he was an eminent priest. And so he proposed this meeting he proposed this primeval atom model at a meeting of the British Association in 1932. How did contemporary physicists react to this idea? Einstein: your mass is correct, but your physics is abominable. Remember, Einstein still believed in the static universe. Eddington, who was another great cosmologist and astrophysicist, philosophically, the notion of a beginning of the present order of nature is repugnant to me. This is because he was very religious. He was a Quaker. And he realized that if the universe had a finite beginning, this was bringing about a sort of connection between physics and theology, which he wasn't comfortable with. He preferred the universe not to have a finite beginning because he wanted to keep physics separate from theology. He was a religious person. But anyway, the lesson: don't be deterred by the opposition of great scientists. They were the greatest scientists of the day, but they were wrong. And Lemaitre was right. Now, there were many other steps, I can't go through all of them, in the history of cosmology. One of the great triumphs of cosmology is to realize that a few minutes after the Big Bang, we have a process which is called cosmological nucleosynthesis, which is when hydrogen starts burning into helium and other light elements. And one of the great triumphs of the Big Bang picture, why we believe it, is because we can predict how many of these light elements are produced. And the people who worked on that were called Alpha and Herman. How did people react? Other physicists? They weren't interested. Cosmology was then a skeptically regarded discipline, not worked on by sensible people. This is 1946. But all they were doing, they were applying known physics to the cosmological context. The lesson: always be prepared to apply known physics in new domains, because that's quite a lot of what physics depends on today. Then in 1966, they discovered the background radiation, which surrounds all of us. It's the relic from the early stages of the Big Bang. It was discovered by Penzias and Wilson in 1965, in fact, and that was really the clinching evidence for the Big Bang picture. Since then, everyone has believed in the Big Bang. So it's the expansion of the universe, the cosmological nucleosynthesis, and the discovery of the microwave background. They were the 3 kilobits of evidence. And now this has been studied by many more sophisticated experiments, in particular by satellites. On the left here, we have what was called the WMAP satellite, and on the right, we have the European satellite, the Planck satellite, so-called, named after the physicist Planck. And I won't go into the details, but the color represents the temperature. The microwave background has a uniform temperature of roughly 3 degrees, in fact 2.7 degrees, so it's the same everywhere. But it's got little fluctuations, which are very small, about 1 in 100,000. And those fluctuations are what eventually give rise to galaxies and us. So at this stage, we've developed what you might call the cosmocentric view. Now, it's important to realize that when you observe the universe through light, you're looking backwards in time because the light travels at a finite speed. So if you're looking at a galaxy a million light years away, you're looking at it when it was a million years in the past. So when you draw this picture here of the cosmocentric view, we're in the middle, and when we look at shells of greater radius, we're looking to basically back in time. And so when you look at this so-called cosmic background radiation, you're looking back to a time which is something like 400,000 years after the Big Bang, which is much, much less than the current age of the universe. But you can think of that as a shell, which is colored like the picture in that WMAP picture there I showed earlier. And the beginning of the universe itself is actually even earlier than that. That's at t equals 0. But that just corresponds to a little bit further on. The furthest we can see is this background radiation. And of course, we can see all the galaxies which form after that in shells at greater and greater radii. So I hope that's clear. That's what we mean by the cosmocentric view. But the point is, it's a little bit different from the standard picture because you're looking back in time. It's what are called here cosmic spheres of time. But this raises the question, what happens beyond the horizon? The horizon is the distance light has traveled since the Big Bang, which, if it's 14 billion years, roughly 14 billion light years. No one's saying the universe doesn't exist there. It's just that's as far as we can see. So what happens beyond the visible horizon? Well, there was a remarkable development in the 1990s which elucidated that. It was discovered that the expansion of the universe is accelerating. Now, you would normally expect the expansion of the universe to slow down because of gravity. The galaxies are moving away under the impetus of the Big Bang, but gravity is going to slow them down because gravity is the galaxies attract each other. But people were very surprised to discover that actually the expansion was accelerating. And this had actually, in principle, could have been predicted by Einstein because there was a term in his equations called the cosmological constant, which would cause matter to be repelled. So Einstein could have predicted the cosmological expansion, and he could have predicted the cosmological constant, but he didn't. Well, he thought the universe was static, and in fact, he introduced the cosmological constant to have a static universe. When it was discovered that the universe was expanding, he realized this was a mistake. He realized he could have predicted the expansion of the universe. And he said the cosmological constant was his biggest blunder. He said he should have made it 0. But then they did, and for many decades, everybody assumed it was 0. So when they discovered the universe was expanding, it suggested there was a cosmological constant. So Einstein was right all along. So it was a bit of an irony. So the lesson you learn from this, majority opinion and expectation is often wrong. Majority opinion being Lambda is 0, which Einstein himself had argued for a long time. But Lambda was there. Now, this was tremendously important. What is this? What's causing this expansion? This accelerated expansion? We think it was a sort of cosmological constant, which in some sense represents, we sometimes call dark energy, and it represents the density of space, the density of the vacuum, sometimes referred to as the unbearable lightness of nothing. And we don't know for sure that's what is causing the acceleration, but it's the most natural explanation. And it's important to realize that the same vacuum energy was causing an acceleration in the much earlier phase of the universe, in the early stages of the Big Bang, and it's then called inflation. So inflation is a short period well, a tiny fraction of a second after the Big Bang, when the universe was expanding exponentially fast rather than just as a simple power law. And it's the same vacuum energy which was causing that inflation, that is, causing the acceleration today, except it's at sort of residual vacuum density. Now, and so as cosmologists, we now realize that actually most of the universe is dark. Roughly speaking, something like 27% of the universe is dark matter, something like 5% is ordinary matter, which we can see, people like you and me, and then most of the energy of the universe, 68% according to this, is in so-called dark energy. But the irony is that we don't actually know what the dark matter is or what the dark energy is. We all work on it. I have my own favorite candidate. I like to think it's black holes for the dark matter. And we like to think the dark energy may be something like a cosmological constant. But we don't know for sure. So there's a lot to learn still in cosmology. But what's interesting is that if you believe in inflation and you believe in this dark, what's called cold dark matter, you can predict what the temperature fluctuations are in the microwave background. And what was remarkable is that when those satellites went up, WMAP and Planck, they could measure the temperature fluctuations. And when I say the temperature fluctuations, I mean how much the temperature varies as a function of angular scale. So in this diagram here, I hope it's not too technical, it's the temperature fluctuation as a function of the typical separation between 2 points in the sky. And it has a particular prediction. Inflation and the so-called cold dark matter picture predicts what that form should be. And they measured it, and that's what they found. And it's remarkable, and the precision is remarkable because theorists had predicted this as a result of 10, 20 years of work. Inflation theory plus dark matter tells us what that curve should look like. You put a satellite up in the sky and you measure it, and it looks identical. And if you're a cosmologist, it's amazing because this was all in your head, and all of a sudden it's there in the sky. Of course, that's true of physics in general. You have a theory and suddenly it seems to be correct. But anyway, that's tremendously exciting. But there's an even more important implication. If you believe in the inflationary theory, the question is, you remember, what exists beyond the horizon? Well, according to inflation, our universe is just part of a bubble. And you can see it in this diagram here, where the little red patch, part of a bubble. But not only that, there are lots of other bubbles, which, if you like, are lots of other universes. You can argue about what you mean by a universe. So what it's saying is that the observable universe is just a minuscule part of a far larger physical reality. Now, so really, that has completed my outward journey. And I want to summarize it by going back to the cosmic Uroboros. So let's just go through this now rather quickly. The outward journey. We have the geocentric view, the heliocentric view, the galactocentric view, the cosmocentric view, and the multiverse. So that's the first part of the journey. Let's now think about well, first of all, let me just summarize the results of this outward journey. You could say it's a triumph. We've learned all these amazing things about the universe. But it's come at a price. But here are the important messages. First of all, what we call the universe is always growing. Okay, we started off thinking it was just the planet, then we realize we think it's the solar system, then we think it's the galaxy, then it's the universe, and now it's the multiverse. As it does so, the domain of science is always expanding. At every stage, the more conservative scientists are going to say, you can't, this isn't science, this is philosophy. But at every stage, they've been proved wrong. But science has subtly changed its nature so that that is true. Now, the downside, of course, is that humans have become increasingly insignificant. Obviously, we're completely insignificant in terms of scale. You know, our star is just one of 100 billion stars, and a galaxy which is one of 100 billion galaxies in the universe. And we're also insignificant. I mean, humans have only existed, whatever it is, for a few 100,000 years. We could be wiped out in an instant, you know, if we get hit by an asteroid or a marauding black hole or something like that. And that's assuming we don't wipe ourselves out first. And the other thing is, the heavens have been stripped of divinity. Remember, to the ancient Greeks, the heavens were that was the domain of the divine. That's why they never changed. Well, we've now really looked all the way back to the Big Bang, and there doesn't seem to be any sign of God or the divine. So in some sense, this scientific triumph has come at a price, for some people at least. We're very insignificant, and God seems to have gone. And this is rather represented in these quotes here. David Linney was a former student of mine, actually. I didn't teach him this, but he said, "We humans are just crumbs of organic matter clinging to the surface of one tiny rock. Cosmically, we are no more significant than mold on a shower curtain." And here's another one I quite like. This is a cosmologist at work. "If my work helps just one person feel like a tiny, insignificant speck lost in a cold, uncaring universe, then I'm doing my job." Now, let's go on the inward journey. Maybe we'll find a consolation there. Well, people started looking to smaller and smaller scales with microscopes and accelerators and things. The first thing, of course, they discovered was that solid matter is really made of atoms. And the idea of atoms is very old. It goes back to John Dalton in the 1808. He published his periodic table. But of course, the evidence came in other ways as well. It came from what's called statistical mechanics. Ludwig Boltzmann realized that you could explain the macroscopic laws of gases and liquids in terms of interactions of billions of atoms. So that gave rise to thermodynamics and kinetic theory. The actual evidence for this, direct evidence, actually came from Einstein in 1905 when he wrote one of his first short papers on Brownian motion and realized that Brownian motion, the random motion of molecules, could only be explained if the atomic picture was correct. But bear in mind that other people had been very skeptical about atoms. Ernst Mach, a famous philosopher, said, this was 1897, just before Brownian motion, he heard a lecture by Boltzmann and said, "I don't believe in atoms." This is rather akin to Leconte when talking about the macro journey. Because Mach said, "I don't believe in atoms because we can't see them." Okay, they're just a figment of the theorist's imagination. Of course, he was wrong, because rather like Leconte had failed to anticipate spectroscopy, Mach failed to anticipate Brownian motion. So the same lesson as I gave before, new observation developments are hard to anticipate. Now, after that, people started thinking about what are atoms made of, and one got to the subatomic view. Now, the first picture of the atom was not the correct one. It was the plum pudding model of Thomson, which basically said the atom has got all these negative charges smeared inside a sphere, a plum pudding of positive charge. That turned out to be wrong. The correct picture was the Rutherford model, where, of course, you have a central nucleus and the electrons orbiting around the outside. Rather like, you remember the picture of Captain's model of the galaxy turned out to be a little bit wrong. But it was a first step. And then once we knew that you had nuclei in the middle of a galaxy, so that in the middle of a galaxy, in the middle of an atom, once we knew that the atom was basically empty space, then people started wondering, well, what is a nucleus, the protons and neutrons made of? And then people got to realize they could be made of smaller particles called quarks. And then we got to what's called the standard model of particle physics, which besides all the quarks and various particles like the gluons and the W and Z bosons and things, you have the famous Higgs particle, which gives everything mass and was later discovered. And then people have gone beyond the standard model, but not yet got the evidence. There's a search for what's called supersymmetry. This is an image of the Large Hadron Collider. According to some of these models, there should be a whole family of particles associated with supersymmetry, which haven't yet been discovered, which is a bit of a crisis. And then even higher energies, because you have to go to ever higher energies to probe smaller scales. At higher energies, you have what's called M theory. And M theory says that this is our final theory of physics. And I'll come on to that again a little bit later. But M theory is meant to be the final theory of physics. But again, there's no observational evidence for it. And this causes a lot of people to be very critical. Here is a book by Lee Smolin, who's a friend of mine, so I'm not being overcritical. He wrote a book called The Trouble of Physics. This book criticizes string theory, that means M theory, since it has yet to come up with a single prediction that can be verified using any technology likely to be feasible within our lifetime. So what Lee is saying, he's saying these theories are mathematical. It's got no connection to physics. It shouldn't be called physics because we haven't got any experimental evidence for it. Well, it's true, but I don't agree with the criticism because who's to say whether we just have to be patient and wait for the experimental evidence. It's exactly the same criticism of the multiverse that we don't have any experimental evidence for the multiverse. Now, I should also say that the great thing about particle physics is that it's come to understand the various forces of nature. We know about gravity, but there are also other forces. So I'm just going to give you a very quick history of the unification of the forces. We know there's the electric and the magnetic forces, which are unified in the electromagnetic force by Maxwell and Faraday. There's the weak force, which is associated with radioactive decay of nuclei, and that was unified with electromagnetism by Steven Weinberg and others. That's called the electroweak force. And then there's the strong force, which also operates between nuclei, and that's supposed to be unified with electroweak force in what's called the grand unified theory. And that might, for example, be associated with Gerhard de Hooft, who was a Nobel physicist who's still alive. But the final aim is to unify that with gravity, the force discovered by Newton. And M theory is just the name of the theory, which is currently our favored model for getting a grand unification. This is a picture of Ed Witten, who's a very brilliant physicist, sometimes said to be the biggest brain on the planet, well, at least among physicists. But the key point is, this means that physicists think they're close to having got a theory of everything. The final theory of physics. Now, I'm rather skeptical about that, because after all, it's only a theory of particle physics. Nevertheless, that is the dream. And in particular, Thomas mentioned I did my PhD with Stephen Hawking. That was me when I was at Caltech with him in 1975. But I'm sure you're aware, Stephen's dream was to find a theory of everything. And you may recall a few years ago they had the film, The Theory of Everything, which was based on his love affair with Jane Hawking, his first wife. And in fact, myself and Mari went to the premiere of that, which was exciting. I'd never been to a premiere of a film before. And I sat next to Stephen because he was a good friend. And I was watching his reaction during the movie. And he enjoyed the movie. And I always imagine the newspaper headlines the next day: Stephen Hawking finds Theory of Everything enjoyable. But actually, it struck me, this is very ironic, because this movie was really not about the physics. The movie was about his love affair with Jane. Now, the one thing a Theory of Everything is not going to explain is have a love affair. Because indeed, the whole point about the theory of everything, it's really just a theory of particle physics. It's not a theory of everything at all. That's the point I'm going to come on to later. Now, the key point about this, the forces though, is that they connect the micro domain on the left and the macro domain on the right. Maybe this is a little bit technical, but for example, the same electric force which determines the structure of a solid object like a mountain is also what holds the electron on orbit around the proton. The same strong and weak forces which operate between nuclei are what determine the generation of energy in a star through nuclear burning. The same electroweak force, which we can study in accelerators, may be connected with the dark matter, which surrounds galaxies. The granularified force, which is associated with the highest energy, may be associated with those fluctuations in the background radiation, which eventually give rise to galaxies. And so this link, another lovely feature of this Uroboros, it shows this link between the micro and the macro domains. And the Big Bang, in some sense, can be thought of as the culmination of this connection. You might ask, why does the head of the snake swallow the tail? Well, the reason is this. Remember, when you look at great distances, you're looking back in time. So when you look back 14 billion light years, 14 billion years into the past, to a distance of 14 billion light years, the universe was very, very, very small. That's why the very large meets the very small at the Big Bang. So it's just a beautiful image. Now, and of course, you've got M theory and the multiverse represent the top left and the top right. And so in some sense, the Big Bang, if you like, I can represent, if I blow up the top where the head meets the tail, this is what it looks like. There's the Big Bang where the micro domain hits the macro domain. That's why the very early universe is actually a laboratory for testing the highest energy physics. Now, so going back to the cosmic Uroboros again, we've gone on this inward journey, and I'll just summarize the inward journey again now, like I did before. We've got first the atomic view. We then have the view of the nuclear view, the standard model with the Higgs boson in the middle, the search for supersymmetry, and then the final M theory. So that's our inward journey. So what's the result of the inward journey? You notice that we've got this famous picture here with the little man looking out, I think it's a man, looking out to the left. Well, the inward journey has also shattered our view of reality. Here's a quote from Steven Weinberg, who I mentioned. The more the universe seems comprehensible, the more it also seems pointless. So, although it's a great triumph, again, what is the role of humans? What is the point of the universe? And we've also realized that we're just as vulnerable to destruction from the world within as the world without. I'm talking about nuclear explosions, coming from the smaller scales, or indeed viruses like COVID. Now, I think what I'm doing, because I'm low on time, I think I'm going to skip some of these next slides. Well, rather, I'm going to go through them very, very fast, okay? And then you can ask questions about them. I've talked about the different levels of structure on the small and large micro and macro scales. Underlying the description of physics, of course, many other background concepts. So I was going to first of all talk about the Newtonian view. Now, in the Newtonian view, which prevailed for 300 years, reality is basically, physical reality is three-dimensional space, and there's time. Space and time are absolute. As you know, well, both space and time are absolute in this picture. Clocks always are the same for all observers. When Einstein came along in special relativity, he realized that the arena of physical reality is four-dimensional space-time. And I can't get into the details, but basically different observers moving with different velocities, they sort of have different space and time axes, but everybody agrees on the speed of light. So time is essentially a fourth dimension. And objects like people, they correspond to world lines in this four-dimensional diagram. And there are all sorts of weird things like the twin paradox, where you go off at high speed and you come back and you've only aged 10 years and your brother has aged 1,000 years, things like that. Then he had his theory of general relativity, which says space-time is actually curved, which is obviously a rather complicated concept, but this explains gravity. And then associated with that are a host of other weird phenomena. Black holes, I'm not going to go through this in detail, wormholes, and the message I'm trying to get across now is there are lots of weird ideas that come out of physics. But then we get on to quantum theory, where there are even more weird ideas, and I know you had a meeting, a talk here on quantum theory, so I don't have to say much about that. I think you probably all understand quantum theory now, at least you understand all the puzzles. There are many weird things associated with quantum theory. Particles are not solid objects, they're described by wave functions, so that until you actually make an observation, you don't know what state it's in. So if I toss a coin, it's a superposition of heads and tails until I actually look. There's the famous two-slit experiment where, in some sense, the photon seems to go through both slits at the same time, depending on what observation you choose to make. There's the famous Schrödinger cat experiment where the cat is both alive or dead. I'm assuming maybe you heard about this at the previous talk if you were here. And there's the famous entanglement, which says that objects can be entangled at some great distance, even though in theory they can't communicate. Now, I'm not going to talk about those things in detail. I just want to get across the idea that it's weird. Quantum mechanics says the world is really weird. And I'll just quote a little joke I like by Woody Allen about quantum mechanics. A guy goes to a psychiatrist and says, "Doc, my brother's crazy. He thinks he's a chicken." The doctor says, "Well, why don't you turn him in?" The guy says, "I would, but I need the eggs." Well, the point is, quantum mechanics is just like that. It's crazy, but it works, and we need it. Now, even more weird ideas, and I'm going to do this really quickly. In physics, you have the idea, I've talked about Einstein having four-dimensional space-time, but also there are more complicated possibilities, even more dimensions. Kaluza and Klein realized that they could unify gravity and electromagnetism by invoking a fifth dimension. Now, the only trouble is that this fifth dimension is wrapped up on a very, very small scale, so you can't see it. So I try to represent this here. Along the the long axis are the 3 dimensions of space, and the 5th dimension is wrapped up very small, so you can't actually see it, because it's smaller than the wavelength of light. So from a large distance, you don't see it. But it's there, and that explains electromagnetism in a geometrical way. Now, that was in 26, about the same time as Hubble discovering Hubble's law. But actually, the people forgot about it because they were more interested in quantum theory. But then in the 80s, people realized they could extend this idea. By then they realized there were many more forces in nature besides electricity and gravity. And superstring theory came along, which said there were 10 dimensions. By the that's 10 dimensions, meaning the 4 dimensions of space and time, and 6 extra dimensions, which are all compactified, so you can't see them. They're compactified on roughly what's called the Planck scale, which is that scale at the top left of the Uroboros. Now, actually, there were quite a number of different versions of M theory, but then, of string theory, but then M theory came along in 95 and said we can merge all these theories if we add another dimension. So we have an 11-dimensional model. So you can see that you've gone from 4 to 5 to 10 to 11 dimensions. It sounds crazy, but that's the theory which many physicists think is the way of unifying all the forces. So the history of the higher dimensions in physics is physics basically gives a sequence of paradigms with increasing dimensionality and increasing remoteness from common sense reality. So here it is going from Newton, Einstein, Kaluza-Klein, superstrings, and M theory. So that's the price you pay for unification. And there's another theory which I particularly like. It's called the Randall-Sundrum picture, which says that our physical world is just, it's called a brane, B-R-N-E. It's like a slice in a 5-dimensional bulk. That's B-U-L-K. That's just one version. Now, I'm describing this because I want to get across the fact that there's some really weird ideas in physics. And this will be relevant to the final message of my talk. Now, I want to talk next, though, to my chairman, Thomas. I'm coming up to the hour, but I haven't got... Can I have another 10 minutes? Is that possible? Let's see how it goes, because there is a discussion afterwards. Because the point is, I've only built you up to describe the triumph of physics, okay? Because why I love this diagram, I'm a physicist, I'm passionate about physics. It describes the triumph of physics in coming to understand the world. But the main point of my talk is that actually there's something missing. Because what's missing from this diagram is any reference to mind. It represents the triumph of mindlessness, whereas, of course, there's a lot of emphasis on mindfulness nowadays. And yet, for me, I feel that mind is a fundamental and not an incidental feature of the universe. So how can the theory of physics be complete when it makes no reference to me and to you or to humans? And so I like to put this image of the eye in the middle of the cosmic Uroboros. Now, why do I say that? You see, the irony is, of course, down at the bottom of the Uroboros is the brain, and the brain, if you like, is the culmination of complexity. But mainstream science suggests that consciousness is just the excretum of the neurons. The mind plays a purely passive role in the universe. So the laws of nature go on regardless of whether anyone's watching them. And of course, religion, spirituality, and mystical insights are just illusions. And I'm reacting against that. Now, why do I say that mind is fundamental? I'm just going to list the arguments, first of all, then I'll go into a little bit more detail. First of all, it's the comprehensibility of the universe, the beauty of the universe, quantum theory. The Uroboros represents the expansion of mind, something I've already referred to, and the fact that physical paradigms are themselves just mental models. So let me just go, I have time to go through these arguments and the main argument, which I gave a big talk about just yesterday, is the so-called fine-tunings. But let me just go through these very quickly. Arguments for the significance of mind. Comprehensibility of the universe. I'm just going to give some quotes here. This is James Jeans. The universe is more like a great thought than a great machine. When you look at the cosmic Uroboros, it really does, the way everything fits together, the unity, it's somehow, it's like a great intelligence behind everything. I don't want you to think I'm saying that's God, but I'm just saying you get that impression that there's some great, the universe is like a great thought. Dirac, another great physicist of the 20th century, it's more important to have beauty in one's equations than to have them fit experiments. Well, of course, beauty is a feature of mind. You've all seen these wonderful pictures from the James Webb Telescope. Of course, they're providing really valuable information about the universe and about cosmology and about physics. But beyond that, I'm sure you've all experienced the sheer beauty of those pictures. I mean, it's like a poetic experience or an artistic experience. But again, it's the beauty of the universe in some sense. Mathematics. What do we mean by another feature of the universe is the role of mathematics. See, mathematics underlies physics, physics underlies our description of the universe gives rise to life, which gives to mind, which gives rise to mathematics. So there's this curious sort of closed cycle. And I love this quote from Bertrand Russell: the true spirit of delight, the exaltation, the sense of being more than man, which is the touchstone of the highest excellence, is to be found in mathematics as surely as in poetry. And some people say that numbers are as close as we can get to the handwriting of God. It's the miracle of mathematics. On the other hand, I also like the quote of Rumi, who says, silence is the language of God, all else is poor translation. Now, quantum theory, I've already referred to quantum theory, but one reason quantum theory is interesting is, for the first time in physics, it suggests that the observer plays a role in physics. In particular, Eugene Wigner, for example, suggested that consciousness may collapse the wave function. I'm sure you discussed this. It was discussed in the previous talk on this topic a few days ago. This is a lovely image which comes from John Wheeler. The universe starts with a Big Bang, evolves to generate consciousness, and then consciousness contemplates the Big Bang and somehow brings the universe into existence. This is based on the assumption that consciousness collapses the wave function, which is by no means the majority view. It's a minority view among physicists, but at least it's clear that the process of observation is important. Henry Stapp is a physicist who says that, in fact, quantum theory, the consciousness even collapses the way it affects the way it collapses. And David Bohm, who many of you have heard, argues that there's an implicit order which underlies the explicit order of the physical world. So I love this diagram, the Escher diagram of the hand that is drawing itself. So quantum theory in some sense brings physics into, it brings the observer and mind, if you like, into physics, although it's not a complete description. The whole point about the story of the expansion of physics through the cosmic Uroboros is that it shows that this, on the right here, I've shown the range of our knowledge as a function of century, because as time goes on, remember, we pushed the outer and the inner frontiers further and further. So you can see by the 21st century, we've almost got to the top. We've seen to the edge of the universe. We've still got a way to go in the microscopic domain. We can only go as far as the end of the line there. But we have theories, of course, that go up to the top. So in some sense, the whole history of physics is an expansion of our mind. And then there is the fact that the whole question of, if you ask, what do we mean by matter, you can see the whole history of physics is progressively demolishing our common sense notions. And in some sense, what you've got is a series of mental paradigms. So classical theory, what do we mean by matter? What do we mean by physics? Classical theory says matter is solid. Atomic theory says it's mainly empty space. Special relativity says matter is energy. General relativity says matter is Kerr space-time. Quantum theory says that matter is a wave function. Higher dimensions says that matter is a slice on a brain. Quantum theory goes beyond space and time altogether. I've not really spoken about that. So basically, these paradigm shifts are basically a sequence of mental models. So it's so ironic to say that physics shouldn't be interested in mind. Physics is providing mental models. Now, the best argument, which I'm not going to talk about because I don't have time, but also I spoke about it yesterday, is actually the anthropic principle. There are amazing fine-tunings between the constants of physics, which seem to be required to have observers in the universe. And so I just say what the anthropic principle is. There was the anthropocentric picture, which of course we started with and rejected with Copernicus. The mechanistic picture, the Newtonian picture, says the universe exists independent of our awareness of it. Humans are irrelevant in some sense. But then the anthropic principle says that some features of the universe are required or explained by the requirement that there should be observers present. And that's what I've been interested with. In fact, when I came to Krakow 50 years ago, this is in some sense when the discussion began, because there was a meeting. At that meeting, Brandon Carter gave the first ever talk on the anthropic principle in 1973. This is the picture of Brandon Carter. And he's still alive, and he's just had his 80th birthday. So this is, besides being the 550th birthday of Copernicus, it's also the 50th birthday of the anthropic principle. And so that's why it's a very appropriate occasion. This is a very appropriate occasion to mention it. Now, I'm not going to say anything more about the anthropic principle because I've run out of time. I think I'm going to quickly go through I was going to talk about the anthropic principle, but I'm not going to. You can ask me about the anthropic principle if you want to hear more about it. I'll just say the interpretations of the anthropic principle, there are these constants of nature which seem to have inexplicable relationships between them, which are required for life, which aren't required for physics. I won't go into the details. The question is, what are the explanations? One explanation is the multiverse. If there's lots of universes where you have different values of the constants, we are necessarily in one of the universes with the right values for life. Another explanation, which is much more philosophical, shows this little diagram which says that you need consciousness to collapse the wave function. And so that's, if you like, is a metaphysical explanation. Obviously, there's also the theological explanation, which says that the universe is fine-tuned because there is a tuner, which you might think was God. So God selects the constants so that we can be here. Obviously, most physicists prefer the multiverse. Me, I love the multiverse, but actually I've nothing against God either, so I don't see why God can't work through the multiverse. But that's, I just thought I should say that. I just want to end up by saying that the real question is, will your fundamental theory of physics, if your fundamental theory of physics is going to actually uniquely determine all the constants, which is what some physicists would like, there is no scope for a multiverse and no scope for the anthropic principle. If, however, the final theory of physics, M theory or whatever, doesn't uniquely predict the constants, in that case, you have to say that the value of the constants is contingent, then you have the concept that there is a multiverse which is naturally going to explain the fine-tunings. I'm biased. I am very much in favor of the multiverse. I think the evidence for the multiverse is these fine-tunings. Now, so I like this picture here. This is Einstein in his dressing gown. I like this because during COVID, I was always in my dressing gown because, we never went out. But anyway, this is Einstein saying, what really interests me is whether God had any choice in the creation of the world. And that is, I think that's where I'm going to, I really want to go to the very last slide. I'm going to skip through a few more slides. So just close your eyes because this is the only way I can get there. This is basically to say that basically physics can't explain consciousness. You need to go beyond standard physics. You need an extended physics. But I think that you need this final theory which is going to marry quantum theory with relativity theory. That's the goal. Whether it's M theory or something else, I don't know. But there will be a final theory. I personally like to think that the marriage of quantum and relativity theory is going to, in some sense, accommodate mind and consciousness. And I could elaborate on that in more detail in the question session if you like. In some sense, that's weird because it's saying it's the end of the matter-centric view. I went through the various geocentric, heliocentric, galactocentric, cosmocentric view. Maybe there's going to be a level of science which goes beyond the so-called matter-centric view to accommodate mind. And I also, in my own approach, I think it might have something to do with higher dimensions, but this is all crazy and ultra-speculative. So what I want to do now, I'm going to go to my final course. There's a question of, is there room for God? I mustn't get into God in this meeting, but I know some of you are interested in that. I've already talked about the possibility that God might be fine-tuning. I prefer the multiverse, but it's a possibility. It's more natural to say that in some sense, God may have provided the equations if you want to believe in God. But what I want to just end up with is the final picture of Copernicus. Because as I said, Copernicus really started us on this journey. So obviously I'd like to wish Copernicus a happy 550th birthday, but I'd also like to thank him for initiating the journey which I've described. And I'm sorry, it's been a bit of a rush journey towards the end, and I must apologize. Like British Rail, the journey always seems to take longer than expected. So apologies for that, Thomas.
Thank you. Yes. Well, Bernard, you've said that the expansion of physics and expansion of mind, expansion of knowledge always comes with a price. In this case, exceeding your talk by 20 minutes is not a big price. However, the price, unfortunately, we all have to pay is we have to, keep your questions. We will have plenty of time for discussion. Like in 10 or 15 minutes, we'll have Bernard to discuss some further questions which I'm sure arose during this talk. And I will promise the audience will have the opportunity to ask them. You'll have the opportunity to elaborate. But right now, let's thank the speaker again. Give him a big applause and a 15 minutes break, just,
I don't mind missing the break because I don't want them to miss out on questions.
Yeah, but we still need some technical break, to install the chairs and everything. And you throat, yeah, okay. Okay, so stay with us. Stay with us. We are back in a couple of minutes. Thank you.